Hello everyone, I'm Norman Wildberger. Today we're going to look at a very simple case of the most important formula in 20th century pure mathematics from my point of view, which is the Weyl character formula. Now it's a pretty sophisticated result, and in general it takes a fair amount of introduction to lay out, but we're going to be able to look at a special case of it, which interestingly has a lot of the general features of the general situation. And in fact, I'm also going to look at the next simplest case up. So we're going to go from SU2, then also to SU3. And there the situation is already quite a lot richer, and we're going to see that the same sort of general approach that I'm going to be showing you applies there. So we're talking about central polynumbers and their algebra. And so let me just review some of the basic ideas there, some of the terminology. So we introduced symmetric polynumbers Bn, which is the multiset n bar n, which is our interpretation of that is alpha to the minus n plus alpha to the n. So it's a polynumber, but it has also negative possible exponents. So n here can be an arbitrary integer. And the way we want to think about this is not as a function, but rather as a pair of densities, so like point densities, or maybe like Dirac delta functions if you're a physicist, sitting at n and at n bar or minus n. And then the alternating one, very much like at n bar anti and n, so this represents the polynumber minus alpha to the minus n plus alpha to the n. So this one is anti-symmetric, this one is symmetric, or alternating. And we think of that as a pair of densities, but one a positive density and the other one a negative density at n and n bar. And then we've already seen these relations, we've already seen in a previous video what happens when we multiply two of these together. So bm times bn is this combination of b's, am times an is this combination of b's also. This am times bn, we get an alternating thing, which is minus a sub n minus m plus a sub n plus m. And then we saw that we could use these things to get these formulas, that if we take a1 times the particular combination b1 plus b3 plus b5, etc., up to bl, where l is some odd natural number, then that is a sub l plus 1. And similarly, if we multiply a1 by the sum 1 plus b2 plus b4 up to some even b sub m, then we get a sub m plus 1. So these are going to be important. We're going to use these. But it's not actually these sort of elementary ones that we're interested in. Rather, we're interested in the central polynumbers, which are naturally connecting to the representation theory of SU2. Okay, and that's what we're ultimately interested in, is a character formula for the representations of SU2. So along the way, we'll say a little bit about SU2 and the three-sphere in the four-dimensional algebra of quaternions. And we'll look at some simplified way of seeing what the Weyl character formula is. But I need to say that there's a bit of a proviso here because of my anti-irrational point of view, I'm not allowed to take formulas that involve implicitly or explicitly irrational quantities. The usual Weyl character formula, as it's usually presented, is such a formula. So I have to reinterpret it a little bit. That's what I'm going to do for you today. So I'm going to give you what I think is actually a more fundamental approach to this very, very important formula. The algebraic objects that we're really interested in are the central polynumbers Cn, and they're defined for n a natural number. C0 is 1, which we think of just as a little delta function at 0. C1 is alpha to the minus 1 plus alpha, just a pair of delta functions at minus 1 and 1. C2 is alpha to the minus 2 plus 1 plus alpha squared. There is its picture. C3 is alpha to the minus 3 plus alpha to the minus 1 plus alpha cubed, etc. And the pattern is pretty clear. So we're starting, if we have C sub n, we're starting at alpha to the minus n and going up to alpha to the n, but going up by steps of 2 in terms of the exponents. So here is the simple baby version of the Weyl character formula associated to the Dynkin diagram A1. So what is this Weyl character formula? In this case, it's giving us a formula for C sub n, as a quotient of a sub n plus 1. That's an alternating Pauling number, divided by a1. That's another alternating Pauling number. That's sort of the simplest alternating one. And we're taking a n plus 1, just one more than the n here. And it's kind of an immediate consequence of the lemma. It's just a restatement of the lemma, okay? Because this Cn here is, like this one here, is a combination of 1 plus b2. This one's a combination of b1 plus b3. So in general, Cn is a sum of b's, okay? It's either starting with 1, like 1 plus b2 plus b4 plus b6, etc., up to bn, or it's starting with b1 and going b1 plus b3 plus b5 through all the odd ones up to bn. And so this is just a restatement of the lemma that we've already put together. So what this does is it connects the world of symmetric Pauli numbers with the world of alternating Pauli numbers. It expresses a symmetric Pauli number as a quotient of two alternating ones. And perhaps you could think about it this way, that the alternating ones are in principle relatively simple because they each consist of just two terms. So even if n is big, a sub n plus 1 just consists of an alpha to the minus n and an alpha to the n with a minus sign and a plus sign. While this one here also just consists of two terms, an alpha to the minus 1 and an alpha to the 1, again with a minus and a plus sign. So this thing here can have actually quite a lot of terms, but we're expressing it as the quotient of two alternating things, each of which is very simple in the sense of only having two terms. Now, an important note to make here is that in this version of things, there are no complex exponentials involved. Okay, this is purely a statement in the world of Pauli numbers. And that, in my view, is actually the preferred way of thinking about what the Weil character formula is really about. It's really a statement about Pauli numbers, although almost every text and every paper that talks about it will not express it that way, would rather use complex exponentials, which is unfortunate and represents, in my view, not really a correct understanding of what algebraically is really going on here. So to solidify this formula in our minds, let's just have a look at some simple examples. When n is 0, C0 is 1, and then the formula is that it's a1 over a1, and there's a1 and there's a1, and the quotient is 1. C1 is alpha to the minus 1 plus alpha. That's a symmetric Pauli number. According to the formula, it's a2 over a1. Here's a2 minus alpha to the minus 2 plus alpha squared over a1 minus alpha to the minus 1 plus alpha. And you see that this is just a relatively familiar high school identity. C2 is alpha to the minus 2 plus 1 plus alpha squared, and that's the quotient of a3, which is this thing, over a1. And you can also check that directly. And if you think about it for a little while, you realize that these formulas are really, in some sense, just variants of the sum of geometric series formula, okay? Which, say, in the simple version is the following: 1 plus r squared all the way up to r to the n, right? The formula for that is as a quotient, minus 1 plus r to the n plus 1 over minus 1 plus r. So what's happening here is very much like that, except that we're sort of shifting everything. So instead of going from 1 to r to the n, we're rather going from minus n to n by steps size 2. Okay, so there's a little bit of a shifting and scaling going from here to here. But you should think about it that algebraically, it's really sort of essentially the same thing as this. So it's actually quite a familiar formula. Now, what's this formula really about? Well, it's about this Lie group called SU2, which is the simplest, or the smallest, compact, simple Lie group, which is sort of like a continuous or smooth kind of group, which topologically, in this case, is pretty simple. It's just a sphere. It's the 3 sphere. And it's useful to think about that correspondence. So let me just very quickly review some things about quaternions. So a reference for this is the famous math problem series 13. Okay, there's 4 videos, but A and B are sort of introductions, and then C and D are about quaternions. Okay, so a quaternion can be viewed as a 4-dimensional object form T plus XL plus YJ plus ZK, where L, J, and K are some quantities or objects that have this algebraic structure, so that the square of each of them is -1, that L times J is K, J times K is L, K times L is J, and in the other direction, J times L, that should be an L. J times L is minus K, K times J is minus L, and L times K is minus J. I'm using L here instead of I for a reason which is quite obvious in a second. Okay, so this is the algebra of quaternions. It's a four-dimensional space, and here's some kind of representation of it. So we have one axis here, which is the axis through 1, okay, and the hyperplane, which is perpendicular to it through the origin 0 here, is the space spanned by the basis vectors L, J, and K. Okay, and they all lie on the unit sphere. So there's actually 4 axes here: the t-axis, the x-axis, the y-axis, and the z-axis. And I'm also showing you the unit sphere here, which is S3. Okay, and the connection with that we can get through this correspondence between this quaternion and this 2x2 matrix. But now it's a 2x2 matrix with complex entries. And so now I'm going to introduce I as the usual I for complex numbers. Okay, so that's why I don't want to use I up here, because this I is different from any of these other units. So we can identify such a quaternion. We can just take the coefficients t, x, y, and z and cook up a 2x2 matrix by having entry t plus xy here and t minus xi here, and y plus zi here and minus y plus zi here. Then if we call this thing alpha and we call this thing beta, then this thing here is alpha bar, the complex conjugate, and this one here is minus beta bar, the complex conjugate of this thing with a minus sign. And then the group SU2 is characterized by it's those things of this kind for which the determinant is 1, the special representing determinant equals 1, which is the condition that alpha times alpha bar plus beta times beta bar equals 1. And when we rewrite that condition in terms of the t, x, y, and z, which you can easily do because this is the quadrants of alpha. The quadrants of alpha is t squared plus x squared, and the quadrants of beta is y squared plus z squared. So this condition is the condition t squared plus x squared plus y squared plus z squared on Q equals 1. That really is the unit sphere in this 4-dimensional space. So it's the 3-dimensional sphere S3. And that's a compact Lie group, so it's closed under the multiplication of the quaternion algebra. Okay, so you take any 2 elements in this unit sphere, you multiply them, you're getting another element in the unit sphere. Now, of particular interest is what happens when we look at just diagonal matrices, ones for which beta is 0. So if beta is 0, then this condition is that alpha times alpha bar is 1. In other words, that alpha has quadrants 1. In other words, that it lies on, it's like in the unit circle in the complex numbers, however, but just expressed in terms of t and x. So it means that t and x, we're just looking at those two coefficients, we're on the circle. So it's actually this circle here passing through 1 and L. It's like a equatorial circle of this 3-dimensional sphere. So those are things of the form alpha 0, 0, alpha inverse, because if alpha is a unit complex number, then its conjugate is the same as its inverse. So we can rewrite it like this. Okay, and the Weil character formula is really describing the characters of the irreducible representations of SU2, and we can think about that in this model of it as it's a conjugation invariant function. A character turns out to be a conjugation invariant function, which means that it's sort of a constant latitude sphere. Okay, so you get all of those, and so the function, the character, is constant on each one of those. So it only really depends on this direction here. So, okay, this is an example of a compact Lie group, and it's the simplest non-abelian Lie group. Of course, the circle itself is also a compact Lie group, but it's not abelian. But this SU2, or the 3-sphere, is the smallest non-abelian compact Lie group. So it plays a really distinguished role in mathematics, but remarkably, or maybe not so remarkably, it also plays a really distinguished role in physics as well. And this story of these central Pauli numbers is all about the characters of this group. So I want to give you just a little bit more of an idea of what this Weyl character formula looks like in general. It's rather an imposing formula, but I just want to talk about it. But before we do that, let's just say a few things about Hermann Weyl, who's a German mathematician who ended up spending quite a bit of time in Zurich, where he actually became friends with Einstein, and also ended up in Princeton at the Institute for Advanced Studies there. And he's a very influential mathematician in the 20th century. In my view, he is the most important mathematician of the 20th century in pure mathematics. So I have no hesitation in saying that. He made contributions in a wide variety of areas, but he was also straddling physics, so he actually made really important contributions to physics. And in fact, modern gauge theory was really something that basically he introduced. So his work that maybe that he's most famous for these days is his foundational work on compact groups and their representations, and the Weyl character formula and other related results in this direction. It was basically a theory that he brought into being, and it became hugely influential in physics and in mathematics throughout the century. But he also did foundational work in number theory, in logic. He had great interest in philosophy and the history of mathematics, and also made contributions to analysis. And notably, also I have a great amount of sympathy for him because he was also skeptical about real numbers. Okay, he could see that there was a problem with real numbers, and he struggled for many years trying to figure out whether he was on Brouwer's side of intuitionism of the Dutch mathematician Brouwer, or whether he was, more on the side of the logicists, because I think he was actually a student of Hilbert. But in any case, he definitely had an idea that the foundations of mathematics were not really in a good state. And he didn't really know how to resolve that, perhaps, but he could certainly identify that there was a problem. Okay, so here is the Weyl character formula as it's often presented. Okay, so without having to describe all of these things, so let me say very roughly that we're talking about a compact group, like you could think about SU2, and here's a group element. And it's written in exponential form so that you're really starting with a sort of an infinitesimal element in the so-called Lie algebra. But you should think about this thing here as being an element in an analog of the circle that we identified for SU2, what's called a Cartan subgroup, okay? So that's a subgroup for which any other element in the group is conjugate to one of the elements in this Cartan subgroup. And so that means that if you understand the character on the Cartan subgroup, then you understand it everywhere, okay? So he's describing the character's values on a particular Cartan subgroup, and he's saying that in terms of this infinitesimal element H in the corresponding Lie algebra, that we have to take some signed sum. So there's a finite group called the Weyl group, very famous, and we're having to sum over the Weyl group, and we're summing some plus or minus ones, and here are exponentials, e to the lambda plus rho, where lambda is some weight which corresponds to the irreducible representation that we're talking about, okay? And rho is some important kind of quantum shift that somehow mysteriously occurs. Okay, and down in the denominator, it's called the Weyl denominator, it's a similar kind of thing, but now there's no lambda, it's just the exponential of e to the rho of WH, but we're still summing over Weyl translates of H. So in the case of SU2, okay, what this sort of amounts to is that here is, for example, a typical character of SU2, say chi3. Which is this central Pauli number, which we're calling C3. So with delta functions at 3, 1, minus 1, and minus 3. And the Weyl character formula in this case is the formula that we've already talked about, but it's this quotient of the A4 over the A1. And the A4 for us, we can visualize that as a delta function at 4 and minus a delta function at minus 4. And so here you see that in this case here, the Weyl group is just the reflection about 0. the Weyl group is very simple. It only has two elements, the identity and this reflection. So there's only two elements in this sum, corresponding to the two elements that are appearing here, one with a plus sign and the other one with a minus sign. And in the denominator, it's the same kind of thing, sum of two elements, one with a plus sign, one with a minus sign, but now we're sort of at the place where rho is in this case a 1. So in this story here, rho, you should think of that perhaps as being that point 1 there, and the lambda is 3. And so this 4 here is the rho plus lambda that's appearing here. So this is a very special and very simple baby kind of Weyl character formula, but it's still an important example because actually many features of the general case are already found here in some sort of simple way. So the beauty of the Weyl character formula is that it extends in a remarkable direction to include all the compact, simple Lie groups. And these are classified, they were classified by Killing and Cartan, at the end of the 19th century, into two unbounded families, the AN family and the DN family. So N is a natural number. And then E6, E7, E8. These are three exceptional ones in the E family, and then two other exceptional ones called F4 and G2. And there's, years of discussion to be had about all of this story. So it's very big and rich thing. And in fact, in my Wild Egg Maths YouTube channel, I have an entire series called Exceptional Structures in Mathematics and Physics, coming from dynamics on graphs, where these things and the corresponding graphs are sort of the center objects in this theory. And I'm looking at everything from this graph theoretical point of view coming from this. So what I'm saying here, I'm going to be very quick, and I'm just going to talk about A2, which is the next simplest example up from A1, up from the SU2 case. But that's already quite rich and has huge consequences for physics. But this whole thing generalizes in some kind of massive fashion, and I'm aiming to explain a good amount of that in that series. So for members of the Wild Egg Maths channel, the series is called Dynamics on Graphs. So in this case here, we're going from the A1 of the former case to A2, which group theoretically is going from SU2, that 2 by 2 matrix group, to SU3, which is a corresponding 3 by 3 group of complex matrices. And this one is particularly interesting for particle physicists because it corresponds to the strong force in the Standard Model. And it turns out that exactly this picture here, which I'm about to explain to you, it's a sort of an aspect of the Weyl character formula in this case here, is really responsible for what's called the eightfold way, introduced by Murray Gell-Mann and in the 1960s, which really sort of set the stage for the modern theory of the Standard Model of particle physics. So what do we see here? Okay, so without going into any detail, what we see is sort of a two-dimensional version of that one-dimensional thing that we saw before. So now there are two dimensions, and you can think about a basis being in this direction and in this direction. So here's alpha. You can think about that as the same Pauli number alpha as we had before. Or rather, we think about a delta function sitting there. Okay, so you think of a delta function sitting there as representing that Pauli number alpha. But now there's a second Pauli number beta in sort of another direction. Okay, and then we have various combinations of them. And in this case, we're going to choose the lambda to be this particular point here, okay, which is like alpha plus beta, and corresponds to the Pauli number alpha times beta. Okay. Now, it's not really a Pauli number, it's really a multi-number. So this story here really makes more sense when we go down one level from the Pauli number story to the multi-number story. It's sort of necessary for us to do that. And part of the motivation of thinking about Pauli numbers this way is to facilitate that movement, okay? To be able to smoothly understand what I'm basically presenting here, for example. But so this is just to give you a rough idea of how the Weyl character formula works. So we're going to take a particular representation. So there's a whole bunch there's unbounded numbers of representations. Basically, each one of these dots in this chamber here corresponds to an irreducible representation. And if we choose that one there, then it turns out that the dimension is 8. It's an 8-dimensional representation. And it turns out that the character is given by these blue circles. One there, and 2 of them in the middle there. Okay. Now, these ones here, okay, these correspond to delta functions corresponding to these integral polynumbers. So this one's alpha, beta. But this one here, you have to kind of go over 2 alphas and then go back a beta. So this one here corresponds to alpha squared over beta, or we could say beta to the minus 1. And then if we keep going on there, this one is alpha beta to the minus 2, alpha to the minus 1, beta to the minus 1, alpha to the minus 2 beta, alpha minus 1 beta squared. And then this one here corresponds to 2 times the identity, so that's just the number 2. So this is the character of this corresponding representation, and it's the fact that this character and this pattern in blue correspond to an octet of baryons that Murray Gell-Mann realized, and also there's a sort of corresponding octet of mesons, or maybe a nonet. But anyway, so it's the correspondence of some elementary particles when you map them in the right way with this diagram here, which was really the start of this version of the standard model. And what the Weyl character formula says is that this is a symmetric polynomial, but now with regard to a group which is a little bit bigger. The Weyl group consists of reflection in this axis, but also reflection in this axis, and in fact also reflection in this axis. So the Weyl group here has the property that if we take one of these points like this one here, then the orbit of that point under all the group actions is exactly this hexagon. In general, it's a hexagon. And what we have on the right-hand side of the Weyl character formula is a quotient of 2 alternating polynomials, or polynumbers, but polynumbers in alpha and beta. And they correspond to the following. So the numerator corresponds to the image of this one here, which is lambda plus rho. So it turns out that rho, whatever that is, it's sort of this mysterious sort of quantum thing. That turns out in this case to also be that one there. Okay, so lambda is that and rho is that also. So lambda plus rho is this one up here. And so if we take the Weyl group orbit of this, we get these 6 points in red. And the Weyl character formula says that we should take the corresponding sort of integral polynumbers, like this one is alpha squared beta squared. This one corresponds to alpha to the 4th beta to the minus 2. This one to alpha squared beta to the minus 4, etc. But we should take an alternating sum, so plus, minus, plus, minus, plus, minus. Okay, so that's the alternating, that's the numerator. And then in the denominator, this sort of Weyl denominator, we get a simpler alternating one, which we just obtaining by taking this rho and doing the same thing to it. So the image of rho under the group is these things here, these 6 ones, and we get correspondingly alternating things, alpha beta for that one, alpha squared beta to the minus 1 for that, alpha beta squared, alpha beta to the minus 2 for that rather. This one is minus alpha minus 1 beta to the minus 1, this one alpha to the minus 2 beta, and this one minus alpha to the minus 1 beta squared. And these the exponents here are just found by vector things. So to get here, you have to do 1 alpha and you have to subtract 2 beta, and that's why this is going to be alpha times beta to the minus 2. It's going to correspond to that term. Okay, so what's happening here is that this character, this is what we're interested in from the representation theory and also from the physics. But Weyl is giving us an alternate way of thinking about what this thing is, as a ratio or a quotient of 2 alternating sums. But here the sums are over just single orbits of the Weyl group, while over here we actually have a sum over multiple orbits of the Weyl group. Okay, in this case, because this thing is relatively small, there's only actually 2 orbits, the orbit of this thing and the orbit of this thing. But if lambda was further out here, then this would be a very, very big expression. Okay, but these ones here are both still relatively simple. They always have a form like this, just with 6 terms here, 6 terms here, but with different exponents. Okay, so there's something very attractive about this form of the thing, but the actual thing that we're interested in is this big thing on the left here, which is the actual character of the corresponding representation. Now, I realize that's all way too fast and really requires familiarity with a lot of other things. So I am going to talk about this whole story in great length and great detail over in the Dynamics on Graphs series in Wild Egg Maths. So if you're interested in that, make sure you head on over there and start catching up on that series. So from the point of view of a physicist, these representations of like SU2 or SU3 roughly correspond to particles or sort of families of particles. And interaction between particles, sort of algebraically, is manifested by tensor producting the representations. That's a little bit sophisticated, to taking products of matrices in somewhat complicated fashion. But it turns out that the characters, the corresponding characters of these tensor products are very easy to deal with. They're just the products of the corresponding characters. So at the level of the characters, the interaction of these particles is pretty simple. That's why the character theory is so attractive and important. And it turns out here then we can make some contact with just the algebra of central polynumbers, because for SU2, if we go back to that, the characters are all of the form C sub n, okay? And so a typical kind of tensor product calculation would be to multiply two of these things and ask, what do we get? So what do we get if we take the polynumber, the integral polynumber C3, and multiply it by the integral polynumber C4? Well, I'm going to do that for you here, okay? So let's see what we get. So of course, I could just multiply this thing out, but I'm going to do it in a more diagrammatical way, which is more reflective of the way I want you to think about these things, okay, as densities. So let's think about, this is the density that we're going to move and translate and put down in various places depending on these values. So at alpha to the minus 3, that's minus 3 there, we're going to take a copy of this thing here and sort of translate it so that it's centered at minus 3. So what does that look like? Well, it means that there's going to be a 1 there, and then we go up 2, and we go up 2, and we go down 2, and we go down 2, okay? So we've taken this thing here and sort of basically convolved it or multiplied it by alpha to the minus 3. Now we're going to do the same thing with alpha to the minus 1. So we're going to take the same thing over here, now translate it so it's centered at minus 1. Okay? So I'm going to put it down on top. So the masses are going to add, so I'm going to do it like that. So now there's another mass there, and another mass there, and another mass there, and 2 on the other side, 1 on that one, and 1 on that one. Okay? And now I'm going to do the same thing with alpha. So we're centered here. I'm going to take a copy of this and plump it there. So there'll be 1 in the middle, 1 on that side, and 1 a little bit further away. And there'll also be 1 here and 1 here. And finally, 1 centered here. So now I'm centering this thing here. So there's 1 there, there's 1 over here, and there's 1 over here. And there's also another 1 on this side, so I'll put it up there. And another 1 on this side here. So that's the end result. Okay, let me just leave it at that, and let's before we interpret this, let me see if we could sort of do this in another way. Suppose we didn't want to actually do the multiplication, but just wanted to use some of the formulas that we already know. So in particular, we know the Weil character formula. We know that C3 is A4 over A1, and C4 is A5 over A1. So one thing we could do is we could look at one of those prior formulas that tells us how to multiply two A's. So A4 times A5 turns out to be minus B1 plus B9. So we could write it like this, minus B1 plus B9 over A1 squared. However, maybe it's not so clear how to interpret that, okay? So yeah, we can do that, but maybe it's not entirely helpful. But it turns out that there's something else that we can do that's sort of halfway to this, okay? Not going the full way, but just halfway. And what that means is we're going to take C4 and replace it with A5, A1. But C3, we're going to sort of leave it as it is and express it in terms of the B's, because we know how to multiply A's and B's, okay? So remember C3, there's C3 there. That's really the sum of, that one there is B1, and that's B3. So C3 is really B1 plus B3. So if we do that, then we can write it as A5 times B1 plus A5 times B3 all over a single A1. And now there's another law that we had also on the first page, which is that A sub m times B sub n equals minus A sub n minus m plus A sub m plus n. Okay, cool. So what is A5 times B1? So we have 5 and 1. So here we have minus 1 minus 5. 1 minus 5 is minus 4. So, but A to the minus 4, or A sub minus 4, is the same as minus A sub 4 because it's alternating. So this minus sign changes to a plus. We get a plus A4, and this one will just be A6. And A5, A3, the same kind of thing happens. The difference is 2. The sum is 8. So we get A2 plus A8 over A1. And now we can rewrite this because, again, the Weil character formula allows us now to rewrite quotients in terms of C's. So A4 over A1, well, that was C3. Actually, maybe we'll start with the smallest one. A2 over A1, that's C1. And then A4 over A1, that's C3. And then A6 over A1, that's C5. And finally, A8 over A1, that's C7. Okay, so that's what we're getting there. And that's the kind of decomposition that's very important, and physicists are doing this all the time, where you tensor product two representations. It's like taking the product of these two representations and then breaking up the sum as a linear combination of other representations. On the character side, it just means we're multiplying two characters and writing the result as a sum of individual characters. Let's compare that to what we got when we just sort of did it with just algebra in terms of densities. You see the C1, where's C1 in this story? C1 is the alpha plus alpha minus 1. So it's that thing there and that thing there. That's C1. And where is C3? Well, C3 is, let me do this one, and this one, and this one, and this one. Okay, that's a C3. And the C5, well, that's that one, and 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 that one. And finally, the C7, it's that one, 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 and that one. So yes, indeed, what we're getting with this kind of streamlined, a clever use of the Weil character formula agrees with what we got longhand. And it turns out that pretty well exactly this thinking applies to the more general situation. In particular, it applies to SU3, but in general it applies to higher dimensional Lie groups as well. So there's sort of famous formulas for decompositions of tensor products, which are basically just elaborations of exactly this technique that I've shown you here in this simplest case of SU2. Oh, great. Okay, so we've covered a lot of territory today, and I don't expect you to have absorbed it all. In some sense, what I want to do really is motivate you, okay, to thinking about the usefulness of expanding our polynumber approach with these integral polynumbers, with negative numbers, both in terms of coefficients and exponents, to the multi-number story, where we have more than just one variable. That's really what's happening in the SU3 case, for example, and happens in all the other cases as well. And I also want to motivate those people who have some background in representation theory to think a little bit again about the Weil character formula. So I'm suggesting that the Weil character formula is really not about exponentials, okay? And the usual angular representation of maximal tori, etc., is not really what you want to do. You want to think about things in terms of polynumbers. It's all just polynomial algebra, people. The Weil character formula is 100% polynomial algebra. And if you've watched this video carefully, maybe watch it a couple of times, and you have some background in representation theory, you should probably be able to sort of to see how that goes. If you're a graduate student, it's a great thing to spend a few months thinking about. I'm Norman Wildberger. Thanks for listening.